You know, a generator rotor built for a marine vessel actually isn't designed for its normal, everyday running speed. It's engineered specifically for the absolute worst overspeed event it might ever have to survive. Welcome to this explainer on stator and rotor construction, where we're going to look at exactly what keeps a ship powered when things go incredibly wrong. It's a pretty common assumption to look at heavy marine machinery and think, oh, it's optimized for the average day at sea, right? But we actually have to flip that assumption entirely on its head. These marine rotors are engineered exclusively for extreme survival. They are built for the worst day, not the average one. Okay, let's dive into this. The very first absolutely non-negotiable engineering rule for these systems revolves around a very specific number: 120%. That's right, the rotor must be fully capable of physically withstanding mechanical stress up to 120% of its rated speed. Because at this extreme overspeed limit, the rotor has to hold together perfectly. I mean, it simply cannot yield to the massive mechanical strain and the heavy vibration that happen during these severe transient events. It's a strict survival threshold, and it honestly dictates every single aspect of how the machine is built. So let's move on to our next hard limit, which is 1.5 times. A marine rotor's critical rotational speed is required to sit at least 1.5 times above the nominal running speed of the generator. Why 1.5? Well, the crucial point here is that this 1.5x margin acts as this invisible mechanical buffer. It basically ensures that the rotor's normal everyday operation stays safely clear of its own resonance point. And you definitely want to avoid that point because it's an incredibly dangerous zone where vibrations can multiply and literally tear heavy equipment apart. Let's do a quick check to see why this mathematical margin really matters in practice. What if a rotor's critical speed is calculated at only 1.2 times the nominal speed instead of that required 1.5x? Like, what is the actual danger there? The answer is a massive, massive resonance risk. You see, during normal upset conditions, which, let's face it, absolutely happen at sea all the time, any speed excursion pushing above 1.2 times nominal would force that rotor right toward its own resonant frequency. And that risks catastrophic, severe vibration damage that could just completely disable the generator. And this brilliantly illustrates exactly why specific physical designs are chosen by marine engineers in the first place. To actually survive these extreme mathematical thresholds without, breaking apart, marine generators utilize what's known as salient pole construction. Let's just deconstruct this rotor layer by layer to see how it works. First, you start with a massive forged steel rotor hub. Next, the salient poles themselves, which are made from punched and stacked steel plates. They're bolted directly to that forged hub. Then, a damper winding is wrapped around it. And finally, the windings are physically supported and cooled by aluminum profiles. This highly specific combination of materials, it's chosen strictly for its high vibration resistance in brutal sea conditions. So, bringing it all together, you now know the definitive design standards for a marine rotor. You've got the two hard mechanical limits, that 120% overspeed survival limit and the 1.5x critical speed margin, combined with that rugged salient pole construction that actually delivers the necessary durability. But, this brings up a pretty fascinating final thought for us today. We've established that the rotor itself is basically an indestructible piece of engineering designed for the absolute worst day at sea. But what happens to this incredible rotor if the bearings that actually carry its weight and keep hidden shaft currents from destroying it, what if they suddenly fail? Well, we are going to tackle that exact scenario in our next explainer on bearings and accessories. See you then?